A is the direction and B is the pulse. We're set at 20 microseconds per division, so that gives us between a drop in the direction is our trigger, and we're getting 1, 2, 3, 4, 5, 520s, 100, and that 120 microseconds before we get our pulse, which is on B. Now if I change the trigger around the opposite direction, I'll just put it on hold first and change the trigger to the opposite direction. There's 20, 40, 60, 80, 100, 120 microseconds before I'm getting the pulse. And change the trigger slope back the other direction. It's the same. I'm just using the jog buttons to move the Z-axis backwards and forwards. I'm on the wee turtle image, which is slow mode, or slow jog. I'm going to change to rabbit, which is fast jog. Do it once more. And it's about the same. 20, 40, 60, 80, 100. And the bits is 120 microseconds. The pulse is more or less the same. If I change that from 20 microseconds per division to 50 microseconds per division. Do it one more time. I'm going back to the turtle slow jog because I'm not able to watch that terribly well and I don't particularly want to crash. So that's 50. It's 120 microseconds more or less between direction change and the first pulse. I'll swap the trigger to the opposite slope. And there it's 120 microseconds more or less. So I'm triggering on a direction change. That's at 50 microseconds per division. We get 100. So that's 120 microseconds, doesn't change. And if I make that faster, it may be possible. That's 200 microseconds per division. So I'm still getting the 120. If I, let me see. .500 microseconds per division. Let's have a look. Okay. Make it 1,000 per second, millisecond. Should I say? Okay, make it 2 milliseconds. I get 5 milliseconds. Okay, now you can see a number of pulses. This one is more or less right on top of it. There's one missing there. Do it again. Still seems to be one missing there. Big long gap and then they get smaller. 10 milliseconds per division. If you get one, you get a gap, and then they seem to be getting closer together. It's accelerating. Starting off slow and accelerating in the jog mode. I'm going to go back down to 5 milliseconds per division. No, I'm on hold. 5 milliseconds per division. I'm going to try that on fast jog. And they're getting closer. It is doing a ramp up. That's 5 milliseconds. 5. So that's probably about 10 milliseconds before the second one. Doesn't matter. Go way down. 1 millisecond, 500 microseconds, 200 microseconds. Go down further, 150 microseconds. Okay, so it's 50. And 50, it's about 120 microseconds. Again on fast jog, I think I've done this already. Or sorry, this is on slow. It's 120 microseconds per division. Okay, what happens if I load a program? It's just waiting for direction changes and then it's triggering on that. Okay, change the slope. Now, I was curious as to whether it behaved any different if it was running a program as opposed to using the jog buttons before I get the first pulse following a direction change. 500 milliseconds, 500 something or others, 500 microseconds. Change the slope again, it's a little easier to see. Okay, that's 500 microseconds per division. I'm going to move it up to 1 millisecond, 2 milliseconds. Oh no. And you see the first and the second trigger there, or the pulse. There's my second pulse. Lots of noise. Could do it filtering a bit of that out, but it is going into an opto isolator, so it shouldn't make a lot of difference. First pulse, second pulse, 5 milliseconds. First, second, third, fourth, fifth. They're accelerating again. Okay, very good. I'm going to let this program run because it doesn't it behaves a bit weird if I cut the program midstream. I have to reset some G codes, I think, but I'm not sure which ones to reset. So I'd have to take out my notes. It's easier just to let it run, though it'll be running for quite some time. There's the lathe reflected on the screen. But you can see where the program is. The little yellow thing has to move all the way out to the end. Or I switch to G code. There's the jog buttons there that I was fiddling around with earlier. There's the buttons on the scope. Okay, B is the direction now, A is the pulse, and that's set at 2 microseconds. So 4 microseconds, but by the time it gets up there enough to turn on the opto isolator, I don't think we're getting the full 4. That's 1 microsecond per division. Trigger slope. Say from that point 1 to 3.6, 3.5, and move it down. And move it up. It's 2 microseconds. The voltage is rising here So I've got more or less 4 microseconds. That's 2 per division. So I've got about 4 down there, but by the time it actually switches on the lead, and I need a minimum of 4 for the motor. So I'm playing a bit close to, I'd like to be able to lengthen that pulse or make it into a square wave. So to be able to, I just wonder, pulse width. 3.74 microseconds. It's coming up with there is the pulse width. Okay, that thing stopped now. Big deal. 3.75 microseconds. 3.76. 3.74. And we need 4. Hi guys. I've been away for a while. I've been fiddling and farting around with circuitry, trying to improve this. Stuff. Trying to figure out what my problems are. Anyway, I built this small little circuit. There it is there. It's you've got a pulse coming in on the stepper motor in there, and I've got a couple of leads attached to it at the moment. That's pulse plus, pulse minus. This is an opto isolator, and I'm taking 5 volts, which I'm getting from this, or I did get from that. And this opto isolator that I'm using has, I think the fall time is 1 microsecond more than the rise time. So I'm getting an extra microsecond in the pulse length from it. And I was going to use that and feed it into a pick. That was my original intention. Or it was more or less to figure out what the hell was going on. What the opto isolator in the stepper motor sees, as opposed to what signal is coming into it. Anyway, I'm scrapping that. Don't want it. And I tried this little circuit. I was using a cap to slow down the rise in the voltage after it falls from getting a low pulse. I was able to drag out the pulse length to about 6 microseconds. But again, scrapping it. Then I tried this circuit. I'm using a little transistor. I don't know if you can see it there. There it is there. So what we got? We got it's the stepper motor, the pulse plus and pull minus. I'm getting about 22 volts after it. The voltage being fed to it is 24.29, which is nominally 24 volts, but let's call it 24.29. 22 volts coming out. I have that funny feeling that rises to It either rises to 23 volts when it's on or drops to 21. I haven't worked it out, but it doesn't matter. I'll check for both. I've got in the circuit, I'm dropping the voltage. I have a resistor in series. Sorry, I have a resistor in series going down to the control board. The resistor, it's down there, is 4.7. I've actually changed it to 4.4. All the rest of them I left at 4.7. I'll just show you where that is at the moment. It's up there, 4.4 volts. It's encapsulated in that bit of sheathing. I have one of these resistors for each of them, so I have 6 of them there. So we've got 4.4 volts, or sorry, 4.4 ohms in series with this. I've put on this little circuitry with a transistor in it. I kind of figured when the voltage dropped, I wanted to take the peak off the drop, and I was able to do that, but I'm not going to use it. I think I was just clipping it. I've got 3.2 ohms there, 3.2 kilo ohms. 1 kilo ohm back to ground. Once this turns on, that'll turn on that transistor and it'll divert through that. But what happens when I use that circuit is, let's see on the scope. So that's with the scope across the pull plus and pull minus on the stepper motor. And I've got 975 milliamps, or millivolts difference. That's the drop. Now if I was to take off this little circuit, let's pull off that signal. Okay, it's gone. Let's see what this scope shows. Now the voltage is, sorry, what am I doing? .550 millivolts. So the drop is different. High is 1.88 volts and low is 1.33 volts. Now, I did the exact same thing the other day and I got different results. There's without the tranny in there. And a 750 millivolt drop. High was 1.28, low was 5.25. And it's still circa 4 microseconds. I'll just show you that. And it's 4 microseconds more or less, but the drop is very low. Now I had a wee look at the spec for the motor. Okay, this is information that I got from a company called Soratec DE. They're German on this particular motor. When I was trying to sort out the alarm problems, it's the only English information I could find on this motor. There's a description. Pulse voltage is 3.3 volts minimum, typically 5 volts, 24 volts with a 3 to 5 k ohm resistor. Let's put down under max 24, 3 to 5 k ohm resistor. The logic signal current is typically 10 milliamps, max 16 milliamps, and minimum 7 milliamps. That is useful information. I'll just go down here. Inductance per phase, not important. Pulse signal. In single pulse direction mode, this input represents pulse signal active at each rising or falling edge, software configurable. It's also hardware configurable. You just flick a switch. 3.5 to 24 volts for pull minus, no, for pull high, 0 to 0.5 volts for pull low. For reliable response, pulse width should be longer than 2.5 microseconds for 200 kilohertz max input frequency. In case of using 24 volt, a resistor 3 to 5 kilo ohm must be connected in line. Okay, and if I go on down, and this is using common anode. So the resistors are all on the downside. VCC is connected to pull plus, star plus, and enable plus. Okay, that makes it harder to connect two inputs from a scope to different places. I can't have the ground connected to pull minus and connected to ground at the same time without screwing things up. Now I'm going to go back to where that information at the start. Typically 10 milliamps, 7 to 16. Now, if I was to go back to this little circuit that I had 4.4 kilo ohms as a series resistor. And then I introduced 3.2 kilo ohms at a later stage, probably just after a nanosecond or two. Let's go to our calculator. We've got 4.4 kilo ohms. Let's try these ones. 4400 inverted plus 3200 inverted equals. Now invert that again. So the two parallel resistors will add up to 1.852 K. Shove that in M plus for a while. Now pull minus, I'm getting 22 volts nominal. So if I put in 22 and divide that by memory recall, that gets us 11.875 milliamps, which is within range. 7 to 16 milliamps. So that's fine, doing no harm. If I was to go back to the 4.4, if I was to take out this circuit as I've taken it out now and go back to the 4.4 kilo ohms in series, 22 volts divided by 4400, that's getting me 5 milliamps. Now 5 milliamps seems a little on the low side. Can I check it? Oh, fuck. Is it normally low? Okay, and there's the two leads connected on the way back to the series resistor after the pull minus, and it's connected to an ammeter, and I'm getting 5.13 milliamps, which is out of spec. It's too low. I need to raise it. So let's lift the camera a little. Now I've got two resistors which are supposed to be nominally 1.5k each, but they come out, if you measure between the two of them, they come out at what the hell do they come out at? Let's do it. So the thing won't work at the moment. Switch our lead back to normal for ohms. 2981 kilo ohms. 2K981. So 2981. Let's shove that into memory just for the moment. Now if we were talking 22 volts, 22 divided by memory recall equals 7.3 milliamps. We're down at the low end. 21 divided by 2981, 7 milliamps. Work with 23 volts divided by 2981. We get 7.7 milliamps. So we're right down at the low end, but we're just about there. So I say all of those 6 resistors, I put them at 4K7 initially because I was concerned about damaging things, and I kind of figured start off high, but high is much too high. So I'm going to drop them to the 3K or 2981 if you prefer. So I'm going to do that for all 6 of them. So I need 12 resistors of 1.5K each. Solder them together or use ferrules, cover them in sheathing, write their numbers on them and fit them. And then hopefully we'll be within range and that problem should go away. I'll just have to monitor for a while and see if it behaves itself. Up until now it was reliable some of the time, and then other times it was like the motor was fighting itself. You could hear a change in sound. Sometimes it wouldn't move at all, sometimes it was struggling. It was like it wanted to go backwards and forwards at the same time. With one of those circuits I was able to stick in a diode and I was able to duplicate what was going on. I didn't film it, but maybe I should. Well, there's no point. It was just a problem. I just want to get rid of it to get on with the rest of my life. Anyway, I'll change these resistors out and hopefully I won't have to open this box again for another long time. This box was just an old second-hand box. Well, it wasn't second-hand to me because I bought it new. I put it in a factory with relay logic and then PLCs and microcontrollers and all that stuff came along, so I replaced it at one stage and I ended up with the box. I have a number of them. So if I'm doing stuff for myself, I prefer to just reuse old stuff. And the fact that it had these extra glands in it was handy. I was able to feed out. I had these signals coming out, which is the red one is ground, even though it's red. The blue is pulse minus. The green and the orange are, the green is direction and the yellow is enable. And then out of here I fed 5 volts, which was handy for checking that opto-isolator thing. I still have that old thing in a bag, those LEDs down there, so that when I turn the motor, they're just indicators. I can get rid of them if I want, it doesn't matter. I can leave them there. But it's the same signals that are generated by that little pick in there to feed the encoder signal. It's not doing any harm to keep it. I may want to break out those signals anyway for indexing. If I want to lock the chuck at a particular number of degrees rather than using the big telly, or I could put in an LCD to be able to get me 5 degrees, 10 degrees, or however many degrees I want, and then put a brake on the chuck to lock it manually so that I can work on it if I've got if I connect a powered spindle to the tool post, which is possible at some stage. Okay, so even with those kind of resistors, I'm still at the lower end of the number of amps required, milliamps required, 7 to 16, but I'm within range, which is good enough for the moment. I don't particularly want to drop the resistance too low, could only lead to problems. But there you go, I have a bit of work ahead of me. I have to reconnect the signals, the pulse signal. I have to take out the little break off bits. They were only just for testing. Change all those resistors, close the box. In case you were wondering, if you've watched more of this stuff, if you were wondering what this thing is here for, it's not to stop dust getting in. That's where I stick in a screwdriver or something to disconnect the Ethernet connection, which comes out the side. There, it goes in through there. But this is in case there's a leak in the roof, just to make sure that I don't get a big dollop of water in on top of all the controls someday, which could happen. Happened in my toolbox at one stage and caused a lot of tools to go rusty. So it's just self-protection. What's that? The Self-Preservation Society. Okay, before I start singing, I better shut up and get offline.